variables. So what exactly is a system of linear equations and two variables? It is, well, I mean, we already saw something like that in the second application from section 1.2. If you haven't seen that video yet, go look at it. Basically, we look at two linear equations at the same time. But generally, we're going to be looking at systems of linear equations, or as the book likes to say, linear systems. So a linear system is a set of linear equations that looks like this. Typically, we want them to be in standard form. Ax plus by is equal to h, and cx plus dy is equal to k, and your a, b, c, d, h, and k are constants, and x and y, as usual, are variables. And what would we like to do here? We would like to find the so-called solutions. So we want to find the solutions to this system, i.e. the values of x and y that make both equations true. And, you know, this is just a bunch of vocabulary, but finding finding the solutions is called solving the equations. So solving means finding the values of x and y that make the system true. The book also uses the terminology solution set. So the book uses the terminology solution set, and this is the set of solutions to a system of equations, or as the book was saying, a linear system. Okay, well, let's look at some linear systems and see different ways that we can try to actually solve them. We in fact saw an example of solving linear systems in application number 2, but let's go through something similar. So let's, the book suggests looking at graphing. And let's see how this works out. What do? We take the two equations and graph the corresponding lines, see where they intersect, and guess what the coordinates of the point of intersection are. Then we verify that these are actually the coordinates of a solution. Okay, so this is kind of an iffy method because it's not really exact. Algebra is better, but at least this gives us some sort of picture. So, for example, let's solve the system 2x plus y is equal to 8, and x plus 3y is equal to 9. Okay, great. Well, to do this, let's graph both lines. And so we're going to hop over to our coordinate plane. There we go. Now we're at the coordinate plane. And let's graph both of these lines. Now, what were the two lines we were looking at? Line number 1, let's call it line number 1, was 2x plus y is equal to 8. And this is actually easy enough to graph using the slope-intercept form, because this is just y is equal to negative 2x plus 8 if I subtract negative 2x from both sides. So this is going to be a line with slope negative 2 and y-intercept 8. So let's plot it that way. It has y-intercept 8 right here, and since it has slope 2, that means that, or negative 2, that means that I go down 2 and over 1, 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 and the line keeps extending like that or whatever. And there we go. So it keeps going like that, and up in this direction it goes kind of like that. There's line number 1. That's a 1. Line number 2 was the line x plus 3y is equal to 9. Why don't we use a different method here? Let's find the x and y-intercepts. To find the x-intercept, we set y equal to 0, and this gives us x plus 3 times 0 is equal to 9, or x is equal to 9. Great, there is our x-intercept. To get our y-intercept, we set x equal to 0, and what do we get here? We get 0 plus 3y is equal to 9, so the 0 is gone. We divide both sides by 3, and we have that y is equal to 3. So there is our y-intercept, and we connect these 2 points right here, and we can, kind of extend it off in this direction. It looks like maybe it goes over there. In this direction, it looks like it goes up there. Fine, that's a good enough picture of this line for me. Now we look for the point of intersection because the point with those coordinates satisfies both, is on both lines. This line is number 2 over here. This point is on both lines, so its coordinates satisfy both of these equations. What does it look like? This looks like the point, well, looks like it's 3 in this direction, and the x direction looks like it's 2 in the y direction. So that's going to be our guess. However, I am only human, even though I'm using a computer to draw this. I'm drawing this by hand. Look, this is not a perfect straight line. This does not look exactly like a straight line. So where they hit might not be 3, 2. We have got to check. So let me erase a lot of the work that I did over here. Goodbye. And we're going to check whether this is indeed true. Okay. So what was the first equation? We had 2x plus y equal to 8. Let's plug in the coordinates of this point into here to see if it's true. So 2 times 3 plus 2, is that equal to 8? Just put a question mark over the equal sign to say, hey, man, is this true? So 2 times 3 is 6 plus 2. Is that equal to 8? Yes. Yes, it is equal to 8. Great. So that makes me happy. How about the other line? The other line was x plus 3y is equal to 9. So I'm going to, again, plug in these values. 3 plus 3 times 2, is that equal to 9? Well, we get 3 plus 6. Is that equal to 9? And yes, it is. Hooray for that. So that means that our guess is correct, and 3, 2 is actually the solution. So by graphing both lines, we see the point of intersection seems to be 3, 2. We verify that this is the case by plugging x equal to 3, y equal to 2 in each equation. This makes both true, so the solution is indeed, we can write it 2 ways. We can write it as the point 3, 2, or we can write it as x is equal to 3, y is equal to 2. It depends on when we're thinking, if we're thinking of it sort of abstractly, or in a geometric sense, we might want to think of it as 3, 2. But if we're thinking of it more as specific values, if x represents some quantity we care about and y is some other quantity we care about for some real application, it probably makes more sense to write it out like this. Now I'm not going to, another way we could have done this would be to put both equations into slope-intercept Slope-Intercept form and equate the equations. So, for example, if our first line was 2x plus y is equal to 8, if I subtract 2x from both sides, which I already did before, and while graphing this line, I get y is equal to negative 2x plus 8. For the second line, I have x plus 3y is equal to 9. I subtract x from both sides, and I get 3y is equal to negative x plus 9. And then I divide both sides by 3. And let's note that when I divide the right side by 3, I have to divide both x and 9 by 3. So I get negative x over 3 plus 3. Okay, now I'm going to set these equal. Negative 2x plus 8 is equal to negative x over 3 plus 3. This 3 annoys me, so let's multiply both sides by 3, which gives me 3 times negative x plus 8 is equal to 3 times negative x over 3 plus 3. I'm doing this to clear the denominator on the right side. So I get negative 6x plus 24. Distribution is equal to negative x plus 9. I just distributed and used the fact that 3 will cancel out with this denominator here. Now I'm going to add x to both sides, which gives me negative 5x plus 24. 24 is equal to 9. And then I'm going to subtract 24 from both sides. And what that gives me is negative 5x is equal to, it's going to be negative 20. If I added, negative 15. Great, if I added 24 there, yeah, okay. So I divide both sides by negative 5. So I get x is equal to negative divided by negative is positive. 15 divided by 5 is 3, so I get x is 3. To figure out what y is, I plug it into, to find y, plug into either equation. And so the first one, say, was y is equal to negative 2x plus 8, which is negative 2 times 3 plus 8, which is negative 6 plus 8, which is 2. Or we could have used the other equation, y is equal to negative x over 3 plus 3, which is negative 3 divided by 3 plus 3, which is negative 1 plus 3, which is 2. So we see that x equal to 2, x equal to 3, y equal to 2 is the solution. Now this is a decent way, both of these are fine ways of trying to figure out what the solution to this system of equations is, but it's not necessarily the best way, and we're going to see some other ways of doing this. So this is the last time we're going to do this.